Okay, let's get started. Is the screen visible?
Yes, sir.
Yes. So let's move on. So last class we had discussed about the relation between atomic radius, lattice constant, and atomic packing factor. Hope you understand this. Any doubt in this section? We'll
No,
solve
sir.
some problems later. Next class we'll solve some problems. Today I'll finish that defects and fine. Let's move on to imperfections and defects in crystals. See, when we say crystals, the basic definition says that crystals are ordered arrangement of atoms, ordered periodic arrangement of atoms. That's how we describe a crystal, right? So this ordered arrangement of atoms, this is a long range order. It is not a short range. It runs into micrometers, centimeters. That's what is expected, right? Long range order means it is not compared to atomic length, atom's length, or the molecular length. It should run a long range. That is when we call it as ordered periodic arrangement of atoms. So when atoms are arranged in ordered and periodic manner, all the atoms are arranged in the same way in three different directions, then we should get a very perfect arrangement of these atoms. But in reality, when we look at these crystals, we do not find a perfect crystal. The ordered arrangement will be there, periodicity will be there, but not always. That means it will be there, it would have maintained for a long range, but everywhere, at every point in the crystal or inside the crystal, you cannot see the same ordered arrangement. There may be some discrepancy. So these discrepancies are referred as imperfections and defects, right? That is imperfections in the crystal structure or defects in the crystal structure. So imperfections are mainly due to vacancies, impurity atoms, and defects, right? Vacancies, impurity atoms, and defects, all the three constitute this imperfection. Now, what does these imperfections influence, or what is their significance? Why should we study? That is the next question. See, these crystals exhibit these wonderful properties, such as the optical and electrical properties. Even the mechanical properties, they are more strong, right? And the electrical and optical properties, so they are irreplaceable, right? So they exhibit this wonderful electrical and optical properties because of their structure. Because of this structure. Structure means basically the physical structure, that is the crystal structure. Because the way the atoms are arranged, that gives them this wonderful electrical and optical properties. Now, in between, within the crystals, at some points or at some places, if this periodic arrangement, the proper perfect arrangement is not there, that means we have to compromise with the electrical and optical properties. Our electrical and optical properties will not be as ideal as we expect, right? Did I start recording?
Yes, sir. Started.
Yes, sir.
Started?
It's been
Oh,
recorded.
Yes, sir.
fine. I always forget. If I forget, please remind. So these electrical and optical and mechanical properties of a material, if it is a crystal, it depends on the imperfections and defects. This I'll explain you by taking an example of, let me give a simple example. You know bands, right? In semiconductors and crystals, metals, you know bands, electric bands. So let us take the case of semiconductors. So we have a band like this, energy band. This is called as conduction band. This is called valence band. How these bands are formed, that we'll discuss later. That itself takes 1 or 2 hours, 1 or 2 classes. Let's discuss. I'll explain it in a simple term. And this is called as EG. That is energy gap or forbidden gap, right? So there are no energy levels in this region. You have energy levels in the conduction band, numerous energy levels, right, like this. And you have energy levels in the valence band, numerous energy levels. So electrons can occupy anywhere in the valence band, and electrons can occupy anywhere in the conduction band. Whereas in between, electrons cannot exist or cannot have any energies that fall in between the bottom of the conduction band and top of the valence band. Do you agree? Yes. Then now what happens? If there is a defect, let's say there is a defect or impurity at that particular local site, that means, see, this conduction band, when I draw this line, right, this indicates this energy is available throughout the crystal. Throughout the crystal, right? It is a continuous energy level throughout the crystal. This is a continuous energy level throughout the crystal. This is a continuous energy level throughout the crystal. That is the meaning of this energy band, right? Whereas in between, there are no energy levels available throughout the crystal. But if there is a vacancy or impurity in the material, at that particular physical site, at that particular location, we get an energy level here. We get an energy level at that here. It may be near to the conduction band, or it may be near to the valence band, or it may be anywhere, depending on the type of the defect and the type of the impurity. Type of the vacancy and type of the impurity, type of the defect. There may be locally generated energy levels at that particular site. Suppose an electron is moving, somehow when it is near the physically, when it is near this site, it will, let's say, it occupies this energy level. Once it occupies this energy level, it is almost like being trapped. It gets trapped. It will be difficult for this electron to either come down or go up, and it will not constitute or contribute itself to the conductivity in the material because it is trapped. The only way is it has to come down, right? It has to emit the energy, come down, and then again re-excite. That is the only option. So these are called as energy levels or energy centers, trap centers. They are generally referred as trap centers in the forbidden region. So these trap centers are originated because of the defects and impurities. Right? What does this trap centers do? They reduce the number of available electrons for the conduction. That means we are losing our electrons which should have been in the conducting state. Right? If we have 10 electrons, let's say 2 electrons are lost or trapped in this region. That means we have net 8 electrons only in the conduction band. That means available number of available free electrons in the conduction band has been reduced because of the traps. And once the electrons are trapped there, they may de-excite instantaneously, or they may be trapped there for a longer time. That means momentarily or for a short range of time, those electrons are lost. We have lost those electrons and they are not available for the conduction in this crystal. So that is the meaning. So this makes imperfections and defects, so that's the vacancies, imperfections, impurities, very important study in the electrical conductivity. Similarly, for optical conductivity also, if you remember, how do you get the optical energy from a semiconductor? If you want electromagnetic radiation to be emitted from a semiconductor, what is the origin and or how it is emitted? Can somebody tell me? Hello?
So can you repeat?
See, in semiconductor, let's say LED, light emitting diode. Okay.
Okay, sir.
Okay. So in a light emitting diode, it is a diode, it's semiconducting material. So if it is a semiconductor, we have a band like this. So in a gets or what is the origin of the light? We see the light, that's it. What is the origin of the light?
Transition of electron from lower band to higher energy band, sir.
That you have to do. You put it the other way. You are right.
So during recombination, the energy is released in the form of light.
Energy is released. Yeah, because of what? Repeat.
Because of the transmission of electrons.
From where to where?
Higher recombination.
Higher energy to lower energy.
Higher
Right.
energy to
Transition
lower
was
energy.
right. Yes, this is the transition of electron from higher energy to lower energy. Right. So this is the emission of electrons with energy h nu. Okay. And this energy is equal to what? Emitted energy. Emitted energy h nu is equal to what? Come on. Look at the diagram and say.
Eg.
Eg, very good. It is equal to Eg. See, you have to build an LED, with blue light. That means you want a LED which emits blue light. How do you do that? Quick, come on.
The frequency should be
Frequency of the blue light is equal
Wavelength
to
should
the
be checked, sir.
energy.
Where you will get the wavelength, convert it to frequency or wavelength, whatever it is. Then you will find out h nu for the blue light.
blue light. Yeah.
Right. Then you will check match it with the different materials which have the energy h nu of the blue light equivalent to their band gap. Right. You choose that material, construct a diode, and you operate it as LED. That gives you blue light. Right. Any doubt here? Simple.
No, sir.
No, sir.
Now, yes. Now I have a problem here. See, this LED is operating. It is emitting blue light. There are some imperfections in this crystal, right? Because of that imperfections, there are some defects. Because of these defects, there are some trap centers. Now what happens? Electrons which were supposed to be emitted from this, that is the bottom of the conduction band to the top of the valence band, some of the electrons, they get trapped here. They get transit here. Okay. Through the thermal transitions or thermal this one. Okay. They get trapped here. Some of the electrons, they get trapped here. You know, after they get trapped here, what they do? It is unstable state, right? Sooner or later, they have to come back. So they come down. They come down. When they come down, what do? They emit radiation with a frequency nu dash. With a frequency nu dash, right? This frequency nu dash, is it same as the blue or different?
Different, sir.
Different.
Nu dash is less
Different,
than.
sir.
It is different. What you are expecting a blue. Blue is coming, of course, but there is also some noise in the form of some other different color, right? There is also noise in the form of some other different color, which is not blue. So you are not getting only blue, but you are also getting some other color in this LED, which is not desirable. This particular thing or discrepancy happened because of what? Vacancies and impurities. Because of the presence of vacancies and impurities, this discrepancy has happened. So these vacancies, impurities, and defects play a major role in the performance of semiconductor devices. Remember, vacancies, impurities, defects play a major role in the performance of the semiconductor devices. Right? Because nowadays we are going towards microelectronics into nanoelectronics. Nanoelectronics. Our device size is in nanometers. Device size is not exactly the device size, but the some components of the device, that size is nanometer. In that case, if we have defects or imperfections or impurities in the crystal, that plays a major role in the performance of the device, because the size itself is very, very less. Even otherwise it affects. But now considering the size is very, very less, this imperfections and defects plays an even more vital role in spoiling the performance of the device. So we need to have a thorough understanding of these imperfections and defects in crystal, and we should know till what extent we can compromise with the presence of these defects and crystals, and we should work at minimizing the vacancies, impurities and defects in the crystals when we grow the crystal, right? These crystals
Sir?
are grown. Yes.
If impurities are there, it will be less, sir. But if there are vacancy, it will move freely, no, sir.
No. Vacancy means it is not electron vacancy, it is atomic vacancy. I'll show you in the next slide. Okay. I'll show you in the next slide. Just a minute.
Sir, in this EC, what is the abbreviation of EC, EV and EG, sir?
See, EC is conduction band edge. It is called as conduction band edge. E is for energy, C is for conduction band. This is called as conduction band edge. EV is called as valence band edge. Right? So EC and EV are called as band edges. Okay? EC and EV are called as band edges.
Sir, EG, sir.
EG is energy gap.
Sir?
Gap. Who is that making that so much of sound? So basically we understood that the imperfections and defects, they cause deterioration of electrical, optical and also mechanical properties. Now let's see what are different kinds of vacancies, impurities and defects. Okay.
Sir, it is as like as hydrogen spectrum only, no, sir.
Which one? Sorry, I didn't get.
Before you told, no, sir, EC and EG from, energy shifting. This one is as like as hydrogen spectrum only, no, sir.
Similar. Just the way electron shifts from one orbit to another orbit, here electron shifts from valence band to conduction band. That is all the difference. We don't have too many orbits here. We only have two different energy levels. That is the valence band and the conduction band. Electrons
conduction to valence or valence to conduction, sir?
They keep, see, you supply energy, they jump from valence to conduction. But conduction band is unstable. So if the sufficient energy is not there, the surrounding energy, thermal equilibrium is not there, then these electrons, they jump back to valence band.
Okay, sir.
Okay. Fine. Clear? Any doubts? Okay, let's move here. See, here, first let us take a case of point defects. Right? That means defects which appear as a point or because of a single point. This single point may be atom or a molecule. So here, under point defect, we have two categories. That is the vacancies and imperfections. Sorry, it is not imperfection, it is impurity. Note down the second point as impurity. Vacancies and impurities. This is impurity. Write this down as impurity, please. Impurity.
Yes, sir, done.
Thank you. Okay, fine. So now this is a perfect crystal, right? You look at this arrangement. This looks like a perfect crystal. All atoms are arranged at their designated places, lattice points, and they are periodic and ordered arrangement. There is nothing what is that? Difficult to accept this theoretically. Now, these atoms, they are all interlinked and they are stuck to their lattice points. Lattice points are the spaces where we find the atoms. So all these points, each atom is attached to a lattice point. So they are all bound to that particular space or location, and they are all interconnected. The interconnected means they have interaction between these. There is interaction between these two. There is interaction between these two, right? So this atom is interacting or bonding with all the neighboring atoms. front also, and the back also. So this atom is interacting with all the surrounding atoms. So it is bound tightly, right? It cannot easily move. Now, what would be the energy of each of these atoms?
Same ones.
Yes, we have a constant temperature. Let's say constant temperature. What should be the energy of these atoms? Same.
Equal energies.
That's what equal energy. That's what we expect, but it is not so. They have distributed energies. All of them do not have same energies. They have different energies, right? So this distribution looks like this. What is this distribution? You studied this before in chemistry, kinetic theory of gases. Maxwell-Boltzmann distribution. Haven't you studied it somewhere?
Yes, sir. Yes.
Yes, sir,
Yes,
we
sir.
have.
In the VRMS and all.
See, yes, exactly. VRMS, what is that? V mean or V average, VRMS, and
Probability
one.
speed, average
Most
speed,
probable, sir.
root mean square.
3 velocities comes.
Speed time.
Very good. So the same Boltzmann distribution, what we apply for the gas molecules, right? We apply it to gas molecule. The same Maxwell-Boltzmann distribution, approximately, not exactly, approximately fits into the energy of these atoms. You take the energy of these atoms, one atom may have energy here, another atom may have energy here, another atom may have energy here. But the maximum number of atoms, yes.
Sir, but in gases, we have 3 different types of degrees of freedom, no, sir? One is rotational, vibrational. But here, only we'll have vibrational because it can move sideways.
That's
How
correct.
can we
You're right.
say?
No. I said this roughly or approximately the energy possessed by these atoms that fits into Maxwell-Boltzmann. Approximately, not exactly. Okay. That is the observed fact. Okay, because it fits. So in the x-axis, we have the energy of the atoms or molecules, what we have there, and the y-axis, their number. Right. So maximum number of atoms have the energies in this region. Fine. That is not an issue. Some have less than this, some have more than this. Now the problem is, here you see, some atoms have a lot more energy than others here in this region. Do you agree? Some atoms have lot more energy, though the number is less. The number of such atoms are less. They have enough energy or much more energy than the rest of the atoms in the lattice, right? So these atoms, what they do, they have more energy, right? What should they do? They try to
distribute the energies.
No, they try to spend it, right? That means their vibration increases. When the vibration increases, they are bound by the atomic bonding to the surroundings. When the vibration increases, their energy is more, vibration increases, there is all chances that few of them may overcome the bonding and they get out of the bonding, right? Once they get out of the bonding, they have enough energy, they get out of the bonding, they see this atom which was here, this atom which was here, which has broken its bond and it has moved here. When this atom moves here, there is a space available here, so this atom starts moving up or occupies this place. See here, this atom from here, it has moved up. So now this atom from here, it has moved to this point. Okay, this is how it happens. So next, this atom which was interior, this has moved here, and this atom, this is an exterior atom, this has moved here and it has settled here. Now this is the final situation what we have in a crystal. So we have one atom which was here. Sorry.
It is a Frankel defect, no, sir.
No, it is not Frankel. Frankel will come later. Frankel and Schottky defect will come later. This is how vacancy is generated. I'm not talking about the this one which moves. I'm talking about how the vacancy is generated. Okay. So here a vacancy is generated. See here, this is a vacancy. There should have been an atom. A vacancy is there. So because the vacancy is there, the energy band which was continuous everywhere throughout the crystal will become discontinuous here, right? At this particular location, the energy will be different from the conduction and valence band. So if an electron or a hole, if it comes anywhere around this region, not exactly at this point, anywhere around, because in this vicinity, around this region, the energy levels are different than the valence and conduction band. So if a hole or electron comes here, it gets trapped in this region. So that's why it shows a different energy level than the conduction or valence band. So this vacancy is created. So this defect is called as vacancies. We are not talking about this one yet. We are not bothered about this one yet. Okay, let's not bother about. We just worry about this one as per our first type, that is vacancy. So a vacancy is created in the crystal. So what does vacancies do? Vacancies disrupt the continuity in the bands.
Sir?
Doubts?
Sir, yes, sir. Sir, can you repeat the reason why it shows different energies?
This you will understand better when we discuss the formation of band structure. Okay.
Yes, sir. Okay.
If you are writing down, I'll repeat. I'll repeat the sentence.
Yes, I'm writing it down.
Write down. See, at the site of the vacancy, the continuity in band is disrupted. The continuity in band is disrupted. And energy levels which are in the forbidden region, and the energy levels which are located in the forbidden region would show up. The energy level which are located in the forbidden region would show.
Yes, sir. Thank you.
Sir, forbidden means that empty one, sir.
Forbidden means EG. Now, write down this. Above room temperature, all crystals have atomic vacancies. Above room temperature, all crystals have atomic vacancies. Full stop. Vacancies exist as a requirement of thermal equilibrium. Vacancies exist as the requirement of thermal equilibrium.
Sir, vacancies exist?
Exist as a requirement of thermal equilibrium.
Sir,
Vacancies
Sir,
introduce. Yeah.
can we tell which atoms will be with more energy and which will be consisted with less, sir?
No, we can't say that. It is the atomic distribution. That's it. That's what we can say. If you take these atoms, you take these. Of course,
Silicon
you
and
can simulate
germanium.
it. No, not that one. Here in this lattice, she is asking. Okay, that we cannot. We can simulate based on different factors, how they crystallize, what is the temperature, how many surrounding atoms they are interacting at a time. Based on that, we can simulate it. But when you take this, we cannot. It just, this is how it is distributed, and it keeps changing. It keeps changing. If this atom has more energy at this point of time, and this has less energy, let's say this has less energy, this has more energy at some point of time. After some point of time, this will have more energy. After some point of time, this will have more energy, and its energy would have increased, decreased to this point. So it keeps changing. There's nothing, no hard and fast rule. The energy just keeps changing, distributing. The energy continuously keeps distributed and redistributed. Okay.
So will that
Now,
energy gradient depends on vacancies, sir? I mean,
come again.
sir, actually, the energy changes are continuously happening, right, sir?
Yes.
Will that, I mean, does vacancies affect that energy gradient, sir?
No, 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 no. Not
Okay,
vacancies.
sir.
Whether vacancies are there or not, this will continuously keep happening. Energy
Okay, sir.
redistribution keeps happening. Okay. Now the third
Thank
point you have to write down. Vacancies introduce disorder in the crystal by affecting. Vacancies introduce.
Sir,
Yes.
sir, you said requirement of thermal equilibrium and continuation, sir. This
Full stop there. Full stop. Next sentence.
and this is okay, sir.
Next sentence. Vacancies introduce disorder in the crystal by affecting the periodicity of atoms.
Sir, vacancies introduce
Disorder in the crystal by affecting the periodicity of atoms. Over.
Yes, sir.
Yes, sir.
Okay, then let's move on to the next one. Did you note this down? Diagrams and all?
Yes, sir.
Sir,
Yes,
sir,
sir.
graph is also necessary, sir.
Yes, sir.
Yes, yeah, graph is necessary. It would be asked sometime. Just in the graph, remember, I'll just give me a minute. Okay. In the graph, you make this as energy. Okay. This as FV, F of V. You don't have to. This as N of E. Make it as N of E. Okay. E and N of E, y-axis.
N of E means, sir?
N of E means number of atoms at that particular energy. Let's say this is E. Let's say 500 electron volt. How many atoms are there at that particular energy? How many atoms are there at this particular energy? That is N of E. You don't have to write this. What is the scale? This one. Don't write the values. Don't write the values on X as well as Y axis. Don't write the values. Just draw the graph. X, Y axis, then E on X axis, NE on Y axis. That's it. Then note down this equation. Equation is given by NV is equal to capital N into E to the power of minus EV by KT. Note down this equation and let me know. I'll tell you what are these terms stand for.
Yes, sir.
It's done, sir.
Oh, very good. So NV is the vacancy concentration. NV is
Done, sir.
vacancy concentration. Capital N is atomic density.
So what is NV?
Small nv is vacancy concentration. Vacancy concentration means number of vacancies in unit volume.
Yes.
Ln is atomic concentration. That means number of atoms in unit volume. EV is energy to create vacancy. Energy to create vacancy. E subscript V, energy to create vacancy. Divided by KT, of course, you know.
Sir, K is constant, no, sir,
Sorry?
Boltzmann constant.
K is Boltzmann constant, T is the
Sir,
temperature.
sir, atomic
Yes.
concentration means you told that number of atoms per unit volume, sir.
Yes,
Vacancy concentration means what, sir?
same. Number of vacancies per unit volume.
Okay, sir.
This EV, have you come across it before? A similar one?
Yes, sir. Activation energy.
Very good, very good, very good. Who is that? I don't have your what is that MS Teams because I'm looking at
Sir,
the presentation.
Arrhenius equation,
Harshavardhan,
sir.
sir.
Arrhenius
Very good.
equation, sir.
Harsha told that. Very good. It's
Yes, sir.
Arrhenius equation. So instead of EA, activation energy, what we call in chemistry, in the what is that reactivity of
A
an
is
atom
equal
or
to A
molecule.
into E power minus A by R.
Exactly. Instead of that, we are using EV here. Clear? So we have all here interconnection between physics, chemistry, mathematics. It's all interconnected. Okay. Fine then. Let's move on to next slide. Point defect in under that vacancy is over. Then we have this impurity. See, impurity, we have two types of impurity. One is substitutional impurity, another is interstitial impurity. In substitutional impurity, all these atoms are of same type. Okay. One of the atom is replaced by some other atom. One atom is replaced by some other atom. So this atom which replaces the host atom, right? These are called host atom. The atoms in gray color are called host atom. Atom in red color is called as substitutional atom or impurity atom. So these host atoms, the substitutional atom or the impurity, maybe it is obviously it is a different atom, different type of element, right? In that case, it may be bigger than the host atom, it may be smaller than the host atom, or it may be approximately equal. If it is smaller or bigger than the host atom, apart from disrupting the change in the electronic band continuity, this also brings in change in the crystal structure, physical crystal structure. Because if it is big, certainly it introduces strain here, tension here. If it is small, that in that case it introduces compression.
So
That
it
means
can
in
create
that case,
attraction or repulsion, right?
no. It normally if it is there, it will be bonding, right? It undergoes bonding with the surrounding atom. Without bonding, it cannot survive. Hey, who is that man? Who is laughing? Okay, without bonding, it cannot survive. Hello? Should I continue?
Yes, sir.
So it would have bonding with the surroundings. That
Sir,
bonding
mute him,
cannot
sir.
change. But no, see, I am in presentation. I have to change it to MS Teams and mute him. Okay.
Okay, sir.
You tell him who is
sir.
that. I will remove him permanently from the group.
He self-muted, sir.
Good. If these things happen, then I'll remove them permanently from the group. They have to come and meet us and take the class from Bangalore. Okay. So now, so this is bonded, right? So bonding means obviously it will be attractive. That is not the issue. But if it is smaller, then that distracts these atoms around here. If it is bigger, then also it distracts the atoms around here. So the structure itself is disrupted, right? It is not the same ordered arrangement. The interatomic distance will be highly changed around this atom depending on whether it is of the same size or approximately same size or bigger size or smaller size, right? So it has two types of effects, right? On the crystal structure around this region, as well as on the electronic bands, right? So here the substitutional impurity is different from the host atom. That is all we need to. So here, see, you see this substitutional impurity, the one in the green color. It is a bigger size than the host atom. Okay. So next we have this interstitial impurity. Interstitial impurity, the crystal structure of there as
Sir,
whereas we find
is the basis?
Right. We find one atom at the interstitial position. So this particular atom which we find at the interstitial position, see here, we find it at the interstitial. There will be interstitial means there will be gap between the atoms. So at this interstitial position, we have this atom. This is at the interstitial position. Okay. This is interstitial position. So these are at the interstitial position, right? So these interstitial atoms may be same as the host atom or may be different, right? Normally, when we say impurity, we do not refer to the host atom at the interstitial, but we refer to a different atom, a different elemental atom at the interstitial, right? Understand? Now note down this quickly and notify me. Let's go move on to next.
Sir, could you please tell definition for
basis?
Yes. Repeat. Definition for?
So can you please tell the points for interstitial?
Interstitial. For
Yes,
substitutional, fine.
Sir, for that no need, sir. Tell for interstitial, sir.
Impurity atom can also occupy void between. Impurity atom can also occupy void between host atoms. Then it is called interstitial impurity.
Sir?
Impurity atom can also occupy void between host atoms. Then it is called interstitial impurity.
Sir?
Yes.
Substitutional means the host atom only itself, no, sir?
No. Substitution means host atom is substituted by an impurity.
Means substitutional means bigger one and interstitial means smaller one.
No, nothing like that. Even in substitutional, size may be different. Interstitial size may be different. Now note down the second point, you will understand. Due to difference in vacancy and size of the impurity atom. Due to difference in valency and size of the impurity atom. Due to difference in valency and size of the impurity atom and host atom, there will be strain in the lattice. There will be strain in the lattice. So this particular statement applies to both the type of impurities, whether it is substitutional or interstitial. This statement applies to both the types. So this statement should clear your doubt off, right?
Sir, will you tell the definition for substitution also, sir?
Substitute, very good. Take it. What is this? If the impurity substitutes host atom directly, if the impurity substitutes host atom directly, then it is called substitutional impurity.
Sir, means interstitial means it is in the gaps, sir, and the substitutional means it will totally replace the host atom.
Lattice point. Substitutional means at the lattice point. Interstitial means in between the gaps, between the lattice points and between the atoms.
Okay, sir. Thank you, sir.
Interstitial is not at any lattice point. Okay.
Sir,
Yes.
so substitutional brings two changes. No? So one is electrical band, and what is the other one?
Crystal structure around that region.
Sir, can you repeat?
Crystal structure around that region.
Yes, sir. Thank you, sir.
See, told in that statement also. Statement says, due to difference in valency and size of the impurity atoms and host atoms, there will be strain in the lattice. There will be strain in the lattice. That means lattice is strained. Lattice is strained means the lattice parameter or lattice constant will not be there. It is same throughout, but around that region, lattice constant is different. It has a slight change. It may be less than or more than the original one. That's what the sentence says. So now the Schottky defect. Schottky defect in this particularly comes into picture in ionic crystals. So an ion pair, anion and cation missing is called Schottky defect. And the right one is the Frankel defect. Where Frankel defect, a host ion is displaced into interstitial. The interstitial ion and the vacancy pair is called Frankel defect. This Schottky and Frankel defect particularly come into picture in the case of ionic crystals.
Substitution.
Yes. Clear? Any doubt?
Once tell the definitions, sir.
Which one you want? Both?
Both, sir. Both.
Okay. Write down for Schottky defect.
Yes, sir.
In ionic crystal, an ion pair. In ionic crystals, an ion pair, anion and cation. Anion missing is called Schottky defect.
So can you repeat once again?
In ionic crystals, an ion pair. Ion pair means one positive, one negative. Missing is called Schottky defect. Okay. Frankel defect. A whole the interstitial ion and the vacancy pair. The interstitial ion and the vacancy pair is called Frankel defect.
Sir, once again, you repeat that Frankel one, sir.
A host ion is displaced into interstitial. A host ion is displaced into interstitial. The interstitial ion and vacancy pair. See, this host ion is displaced. This host ion was here, is moved here now, right? So because of that, one thing is the host ion has moved to an interstitial place, point number one. Second thing, that place it left behind, that is vacant now, right? That is vacant. So these two together are called a pair. These two together are called a pair and referred as Frankel defect.
Yes, sir. Thank you, sir.
Okay, guys. Fine then. Let's meet day after tomorrow. Keep this as it is. Okay. Stop recording.